So we're gonna continue talking about the finite elements, and we've talked about how to discretize, or we didn't really talk about it, right? We talked about how we're gonna have somebody else discretize for us, and then we talked about how to write our solutions on little interpolants that are triangles. Okay. So now what we're gonna do is talk about how do then we set up and solve a problem. Up to this point, there is no problem, right? There's just I can represent a surface by a bunch of triangles. But partly what we want to do is now solve some kind of partial differential equation on this thing. Okay, so I give you the most famous picture in all finite element, the kidney bean. Look at any finite element book and you'll see this kidney bean. This is the representation of a shape you don't want to solve things on. That's the basic idea. I have this shape, and I could say, wow, I got to find my dynamics or my solution on some kind of complicated kidney bean shape. Okay? And there it is. And in fact, this is the problem that we want to think about. And in fact, I'm going to apply different boundary conditions on different parts. Over here, I might have some boundaries. This is S1 on this region between those two dots. Over here, S2. And then I have, let me set this up, on any portion of the domain. On the boundary itself, I have this normal direction. Hold on. Let me get myself together here. I'm just sloppy today. Okay, here we go. Okay, here's my normal direction. And by the way, the normal direction facing outwards, and I usually normally have some kind of XY coordinate system, right? And so I think about, I still have that, and I have some angles here. I think this is theta 1, theta 2. Those are not thetas. Okay. Tell me if I'm wrong on those, by the way. So it's interesting, some of the Greek characters on my PDF on my iPad don't show up. Yeah, I know. What's going on with that? Terrible. All right, but anyway, there's my kidney bean domain. I'm going to get a solution on it. Suppose you're like slow cooking it, and you want to know what the dynamics of how you make a kidney bean soft, and so you got to have water infusing in here, and you want a temperature field in there or something like that. Okay, that is a classic problem. So we want to do that, and so you have very complicated conditions. And in fact, let me write down a prototypical equation we might want to solve. Okay, so there's my domain, and here's what I'm going to solve on that domain. Q non-constant coefficient, it's linear, however. Second order in derivatives in space. So, you know, this is sort of looking a little bit like a Laplace's operator here, but it's non-constant coefficient. So these are generic functions defined on this domain. And let's just make the following boundary conditions. I'm just going to make them hard just to make you think, oh, I can't solve this any other way. Okay? So here we go. One of them's easy. Sorry, this one won't make you cringe. Maybe on one part of the domain, I just specify that U, the field, is just some function G that I specify. But on the other part of the domain, maybe I have something more complicated. And you can see I'm looking at the derivatives, the normal derivatives across the boundary, plus Q du dy, okay, cosine theta 2 plus G1 xy u equals G2 xy, and this is on S2. So you say, oh, well, yeah, that boundary condition got imposed. Okay, derivatives, normal derivatives, fluxes, and the generic functions. It looks painful, doesn't it? If you're not in pain a little bit right now, you're just not trying hard enough. or you're not paying enough attention. So maybe it's okay. If you don't pay enough attention in life, you won't be in as much pain. You could almost quote me on that. Can't you? I mean, almost. That's a theory. I could write that, philosophical theory. I'm a philosophical theorist. I do have a doctorate of philosophy. Dropping, I'm not going to call you swine. I'm not going to say those are pearls. I'm not going to say it, but who knows? All right, so here's the issue, by the way. You're going to solve this. And we have to change the problem, and here's why. We are going to represent solutions on this domain on these little triangles. We want to use simplex methods, right? We want to use these triangles. And by the way, so we're going to make this whole domain with triangles. So when you think about discretizing with finite element, it's automatically going to say, you give me that boundary shape. And what I'm going to do is I'm going to first of all do a polynomial fit around that boundary. So when you think about what you do in finite element, right, you say, can I make this kidney bean fit on a rectangular grid? No, not very easily. But when you start thinking about finite element, you just say, okay, just draw points along here. Follow that along. And then you can start drawing your triangles, right? And then making a domain out of this thing. Now, for every triangle in here, let me draw a big one. We want to approximate the solution as simply as possible, which is just using a simplex element. But when we start approximating with something like this, notice that this governing equation has two derivatives in x, two derivatives in y. So this thing here has to solve, I'm going to construct A, B, and C based upon meeting my neighbors and also satisfying that PDE. But if I take two derivatives in x and two derivatives in y, this is 0. So if I put these elements in here, it's like this has no impact. It's as if it doesn't exist. Now, it may be awesome to pretend, awesome, I don't have to even deal with that because I just made it go away by pretending, by being ignorant. But it turns out that doesn't solve the problem. All right. So you see the problem. I got two derivatives here which are incompatible with my information of these linear interpolants, which if I take derivatives, there's no information carried to this level. So we're going to rewrite the problem. So, or let's put it this way. We have two options at this point. Okay? One option is to rewrite the problem so that I can still use those simplexes. The other option is to say, well, I could use those complex elements, right, and start putting a plus bx plus ci plus d x squared plus e y squared plus f x y. Okay, you've got two options. I'm going to go with simplex. Okay, but if I'm going to do that, I have to figure out how to rewrite this problem. Moreover, at every one of these elements, one of the things I might want to handle is the fact that my solution is going to have discontinuities. What if I have shocks? Suppose I'm heating my kidney bean, and then all of a sudden a big temperature shock wave walks through this thing. That's how you cook a bean. Pressure cooker, you put a shock wave through there. Shock waves have big discontinuities, or not discontinuities. They're not real discontinuities. They have just rapid transition regions, right? You might want to capture that. Okay, so you want to set your problem up to handle such things, how to handle shocks effectively. Okay, so what we're going to do is we're going to write this in what's called the weak formulation. And the weak formulation is going to say, take this and write the whole PDE and its boundaries in an integral form. So I want to sort of, in some sense, integrate this equation up. So I'm going to use what's called a variational principle. And it's not so important that you know it. I'll walk you through it right now. And but you're going to start seeing the cost of doing finite element. The cost of finite element is it requires a bunch of math. Right? Bummer, I know. It sucks, right? You got to do all this math to get this thing out. But that's okay. That's the price you pay for solving on kidney beans. Okay. Yeah.
So over here on this triangle, is it u equals a plus bx plus c?
Yeah.
I mean,
let's call it the u as the I of
So the function we're trying to solve for is a plane on each one of those.
Yep. Yeah, and we're going to basically, what I want to do is you say, I want to write down, express my solution on one of these patches, right? And by the way, the patches have to all, match, so these are all connected together. And by the way,
If you're allowing discontinuities, what does that mean? You're saying rapid transition.
yeah, so I could have if I have for instance, a shock propagating through here, I could figure out a way to impose a discontinuity there. Yeah, and then I have to figure out how to handle that. And well, notice, by the way, these points on the boundaries have to satisfy the boundaries. These points in the interior, not only do they have to talk to each other and make sense with each other, but then they also have to satisfy the PDE. Okay? So we're going to talk about how to do that. So I'm going to rewrite this in what's called the integral formulation. And the variational principle says, look, I'm going to write this in an integral form where I'm going to integrate over the volume that I'm solving on. And I'm going to break down some function here. And these are all going to be, when I use subscripts, they'll denote differentiation partial differential with respect to that variable. Okay? Here's sort of a general way to think about writing this. Let me write it down first, and we'll talk. So what I want to do is figure out a way to write this in an integral form where the function f is a function that conveys the information about the PDE itself in the interior, and the function g conveys information about the boundaries. And the question is, how do I construct f and g? Okay? And what are the constraints I use on this? And the way this is going to work, you're going to write this down so that that PDE minimizes this integral. Okay? That's the way this thing is constructed.